Hi everyone, welcome back to the channel. This question was asked in IIT JEE Advanced 2016 and this is a pretty interesting question. This is a deep question because it involves some of the concepts which are not typically clear to many students. And if you see, IIT JEE has been asking such questions for a long time, and every year they will ask question from SHM or something involving linear momentum, conservation of linear momentum, energy and all that. And therefore, it is very important that all of you, the students, should understand what's going on and what are the deep concepts that are required to solve such questions. So we will solve this question today. And also along the way, I'll be giving you some of the concepts which are going to be very handy, which are not typically clear when you study the subject or even if you have solved some problems. Okay. So let's see what's going on. First, read the question. So a block of mass m is connected by a massless spring with constant k to a rigid wall and moves without friction on horizontal surface. The block oscillates with a small amplitude a. Okay, so it's oscillating with amplitude a with an equilibrium position at x0. So at x0, it is actually the velocity is 0 because it's the equilibrium position. Now consider two cases when the block is at x0 and when block is at x0 plus a. So at x0 plus a, the block will have maximum stretch at that point in time in the spring, right? And velocity will be 0. In both the cases, the particle of mass m, a small mass m, is softly placed on the block and after that they stick together, okay? So we need to find which all are true in the given option, okay? So the first question is, how do we even start solving such problem, right? We get into this kind of a situation. So my recommendation is always start with drawing the picture, drawing the free body diagram, okay? So let's draw the picture first, what's going on. So let's say this is the horizontal surface and I have a spring here and there is a mass m attached, okay? And it is oscillating with amplitude a, right? It's given for as oscillation, okay? So let's pick this point as x0, okay? So let's say this is origin and this is x-axis and this is y-axis, okay? Okay, now there are two cases that we need to consider at x equal to x0 and x equal to x0 plus a. So let's say this is the other case where m is at x0 plus a, right? Okay, and then both the places we drop a particle of mass m here and then we need to find out. So first let's write the obvious, whatever is pretty obvious to all of us. So at this point in time, this is the equilibrium point. So what is the stretch here? Spring is 0 here and velocity or speed is max, okay? So this much is known and at this point the spring stretch is max, right? How much? A, because that's the amplitude. And what is the velocity? It is 0, right? Because it will have to turn back and go towards the equilibrium position. Okay, so these two things are pretty clear. Now let's write the equation, okay? Find out the frequency of the oscillation. So let's first find out everything initially. The equation will be minus kx is the, let's say, spring force, and then it should be equal to mx double dot, which is acceleration. Hence acceleration is minus k by m x. Therefore omega 0 initial frequency is k by m. In fact, you can write this directly also. We don't need to go through this F equal to ma here. Okay, but just to show you how to calculate this. So this is the initial frequency. Now at x equal to 0, x0 at this point, let's call this point P and this point Q. Okay, so what is the velocity? So velocity 0 is maximum, and that is always a omega 0. Now how do we compute this? Again, let's just a short note here. Okay, so what should be the equation of this motion if you have to write? So it will be x minus x0 equal to a sine omega t, right? Why am I choosing sine omega t? Why not cos omega t? Because at t equal to 0, the particle, the mass m will be at x0. Therefore, x should be x0. So if you put t equal to 0, x will be x0. Now, if you differentiate it again, you get a omega cos omega t. Now, this is maximum when omega t is n pi and could be 0 also. So therefore, at 0, the velocity is a omega. That is the maximum velocity. Okay. So a omega 0 and a is given. So this will be a k by m. Okay. So that's the initial velocity. Okay. V0. And now what is the energy, initial energy at x0? So we have, this will be equal to kinetic energy initial plus potential energy initial in spring mass system. And what is kinetic energy? So it is half m v0 square and plus 0, because stretch is 0, right? We know that stretch is 0. Okay, so this is the initial energy, half m v0 square. Now let's solve the problem for case 1. Okay. So case 1, the spring stretch is 0. So how much force is acting on mass m? So at x equal to x0, the force is, the sum of all forces is 0. Because spring stretch is 0, there is no other force. Okay. So when force is 0, which means that linear momentum is conserved, right? This should be obvious. Okay. Now, when I place another mass m here, let's say small mass m, then what happens? Linear momentum will still remain conserved. Why? Because the external force is 0. Okay, at that moment. So what is the initial momentum? It is m v0, and the final momentum m plus m v prime, right? Therefore, v prime will be m by m plus m v0. So this is the velocity right after we place another mass m on top of the bigger mass, right? Okay. So if this much is clear, then let's see what is the final energy. So energy final will be half m plus m v prime square. And we are saying energy final means after mass m is placed on m, right? So this is the final velocity for case 1 when mass has been placed on top of another bigger mass m. Okay, so let's just compute this. So this is just half m plus m, and v prime we know from here is m by m plus m whole square v0 square, and therefore this is half m by m plus m mv0 square. And if you compare it with the initial energy EI, so this will be m by m plus m EI. So this is definitely less than EI, right? So final energy is reduced, right? From here we can clearly state that velocity is also reduced, right? So where is this energy being used? Because some energy is being dissipated. So where is that energy going? So you will see that that energy is going into reducing the amplitude, the maximum stretch. So if you calculate the maximum stretch using this equation, m omega 0 a 0 equal to m plus m omega prime a prime, right? Just linear momentum conservation. What is omega prime? Omega prime is k by m plus m, because so final frequency for the oscillation is km by m plus n, using the same equation here. This equation minus kx equal to m plus m x double dot. Okay. So if we use this one, then we get a prime as m by m plus m omega 0 by omega prime, and which is m by m plus m k by m m plus m by k, and therefore a prime is m by m plus m root under, the a0 is there, a0. Amplitude is also reduced. Okay, so we know three things happen: velocity is reduced, energy is reduced, and amplitude is also reduced in case 1, right? Now let's solve for case 2. Okay, case 2. So what is the observation at case 2? So case 2 is when the bigger mass is at x equal to x0 plus a. So this is the maximum stressed case. Spring is maximum stressed by a, and the velocity is 0. Okay. So when velocity is 0, at x equal to x0 plus a, and the force is not 0 because it is k is 0. Okay. Therefore, linear momentum is not conserved. Okay. So you see this one clearly. Okay. Okay. So energy at x equal to x0 plus a is half k a0 square, because kinetic energy is 0 and it is independent of mass, right? Final energy, right? Therefore, the energy will remain constant. Okay. After placing the mass, the small mass m. Okay. If that is true, then we know that omega prime is k by m plus m after placing the mass m. So energy will be the kinetic energy will be half m plus m v prime square, right? And let's say amplitude is a prime, therefore v prime will be a prime omega prime. Okay, so but the energy is going to be conserved, so half m plus m v prime square is equal to half k a0 square. So this is m plus n a prime square omega prime square equal to k a0 square, and therefore m plus m a prime square into k by m plus m equal to k a0 square, and this will cancel out, k will cancel out, therefore a prime is a0. So amplitude will not change, and that should have been obvious because energy is conserved. So energy doesn't change, right? Therefore there is no energy going in changing the amplitude, hence amplitude will remain constant. But what is the final velocity here? V prime. So it will be a0 omega prime. So a0 k by m plus m. So the velocity is reduced, right? Because if you compare it with initially the velocity was a0 k by m. Okay, now let's go and answer the question. So the first option is the amplitude of oscillation in the first case changes by a factor root m by m plus n, and that is correct because we figured out that amplitude is reduced by this much, right? And in the second case amplitude doesn't change, so where in the second case it remains unchanged. So this is the right answer. Second, final time period of oscillation in both the cases is same. That's correct because finally it becomes root k by m plus n. So this is also correct. The total energy decreases in both the cases. We just saw that the energy decreases only in the first case because it has to reduce the amplitude. Second case, it doesn't change. So this is not the right answer. The instantaneous speed at x0 of the combined masses decreases in both the cases, and that's correct because we figured out that velocity is reduced at x0 and also velocity is reduced here also at x equal to 0, right? So in this option C is also correct. Answer is of course A, B and D. But what is the takeaway? So just to recap, in a spring mass system, at the equilibrium position, the spring stretch is 0, but the velocity is maximum. And you should figure it out using this equation also. But at the maximum stretch, velocity will be 0 because it has to turn back. Acceleration is not 0, velocity is 0, and the force also is not 0. Force is not 0. And here the force is 0. Okay, so therefore we have a case where linear momentum is conserved. So momentum is conserved, right? And here in this case energy is conserved. Why momentum is conserved? Because force is 0. Why energy is conserved? Because that kinetic energy is 0. The only energy is there because of the stretch, which is A, and that is not going to change. So the energy, which is half k square, will remain constant even if you add another mass. and even if the velocity changes, because they will adjust so that the final energy remains same. And if you understood these concepts, then the question was very easy. But of course, this question was really there to test your concept. I hope you like this video. Please do subscribe the channel and also share the video with your friends. Thank you very much. Subscribe and gain access to concepts and tips for doing better in IIT JEE or other examinations. Keep up the great work.